Section 9, matrix operations. So it's more of a notation kind of a section. So we have A1 is the first column of the matrix A, A2 is the second column, etc. And so we can annotate each position. So the 1-1 position here means first row, first column. 2-1 means second row, first column, etc. And so A3-2 obviously refers to the third row, second column. So diagonal matrix is a square matrix whose non-diagonal entries are 0. Classic example is the identity, n by n identity matrix. We'll talk more about diagonal matrices in a bit. So we have three matrices, A, B, and C, same size. So all this is defined, and R and S are just scalars. So notice here we have commutativity of addition. So these seem kind of basic, which is fine. I'm going to go through these very quickly because you're going to see that some basic stuff we're used to we don't get for free here with matrices. So this is distributive, right? This is the additive identity. You can factor the scalars through, left and right, distributive for scalars, and then you can also have commutativity for the scalars in terms of factoring them out. So you can think of matrix multiplication as really just a composition of linear transformations, which seems like it's making something simple more complicated, but it can be useful to think of it slightly differently in this way. So let's say we have a matrix m by n A and B and n by P. Of course, these match, so it's defined, and you'll end up with an m by P for a result. So A has B has columns B1, B2 up to BP. A has all the way up to the little lowercase a, of course. So AB is m by P, as we said, and AB is A times B1, B2, B3. So that's the same as AB1, AB2, etc. So this is just called the row-column rule. We know all this already. If AB is defined, then the entry in the ith row and jth column is the sum of the products of row I of A and column J of B, right? That's essentially what happens when you do the two-finger kind of a thing. So if we want to find the entry in row 1, column 2 of this product, again, this is 2 by 2, this is 2 by 3, so it is defined. We look at the first row of A and the second column of B, and multiplying that out gives us a 0 in that position, in the 1, 2 position. Okay. So again, A, B, and C are matrices of products defined. So we have, again, left distributive for multiplication and addition, and the right are scalar here. Here we have an identity matrix, right? The identity matrix times A is the same as A, or A times the identity matrix. And note that you don't get this for free, right? This is commutativity and multiplication. AB in general does not equal BA with matrix multiplication. Also, you know, with the reals, if the product is 0, one of the numbers has to be 0. Not the case. You do not need the 0 matrix for A or B in order for their product to be 0. So you have to be a little bit careful, and some things that we take for granted or seem kind of obvious with the reals are not so with matrix. Some of the matrix processes in particular, right? This is a big one. So you do not get commutativity of multiplication. Also, there's no such thing as division with matrices, okay? There's something else that we'll get to in the next section. So last bit of definition here. So if we have an m by n matrix, the transpose, which is denoted with a superscript capital T, is an n by m. So you reverse the rows and columns. Okay? So the columns are the corresponding rows of A. So for example, 21 here, if A is A, B, C, D, then the transpose, so this first row becomes the first column, second row becomes the second column. Okay. And as it turns out, there's some interesting properties with transpose. Some are obvious, some not so much. So if you transpose the transpose, of course, you'll get back the original. A plus B transpose is the same as A transpose B transpose, so that's what you would think it would be. You can factor scalars out, doesn't change the fact. This one's a little bit different. So notice that AB transpose is B transpose A transpose. I'm actually going to have you go through a proof of this, and we'll kind of talk about it a little bit. So worksheet, again, just some computation here. Nothing that we haven't really seen before. Here, just a little practice with transpose. So, you know, compute these, and then again, is this defined? Well, probably not if I'm asking, and you'll note why. And then for the homework, a little bit more computation. Here's basically asking you to find a counterexample to that theorem or that rule we discussed earlier, right? We want this is not the identity matrix such that, or the zero matrix such that you do have commutativity, so you want to find a particular one that works. It does work sometimes, not all the times. And then this is what I was telling you about. I want you to prove this. In order to do this, let me give you a little bit of a hint. Think about A in terms of, right, A1, 1, 1, A1, 1, 2, A1, 3, etc. So think about all these positions. Same thing with B. And then take a look at what happens when you multiply A times B. Pick a generic ith row and a jth column, and take a look at that entry and then transpose it and see what happens when you look at these entries. So that's kind of the skeleton as to how to do it. I know I didn't give you a lot there, but if you're thinking in those terms, hopefully that'll be a little helpful. But I do generally end up going over this number 2 with students as it comes up.